Welcome to the new Transatlantic Cable, a tripartite civil engineering history webinar series. The webinars are coordinated by the History and Heritage Committee of the American Society of Civil Engineers, the National History Committee of the Canadian Society for Civil Engineering, and the Panel for Historical Engineering Works of the Institution of Civil Engineers. Today's installment, recorded on May 7th, 2025, features Mike Bartlett on surveying the Canada-United States international boundary.
Hello and welcome. I'm Tanya Kobe-Marking. I am the former chair of the American Society of Civil Engineers History and Heritage Committee, and I'm delighted to be your host today for the tripartite new Transatlantic Cable Civil Engineering History webinar. So our objective today with ASCE, CSCE, and ICE as learned societies, they were developed to maintain high standards of civil engineering practice. And our tripartite new transatlantic cable history webinars support that mission. So we look to enhance the interaction between these societies and their members, and recognize that civil engineering history crosses international boundaries. So the talks that we present in this webinar series are on topics that involve at least two of the participating societies. It is now my pleasure to introduce our presenter, Mike Bartlett. Mike is the past chair of CSCE National History Committee. He is a voting member of the ASCE History and Heritage Committee, and he is the new chair of the American Concrete Institute Committee 120 History of Concrete. Upon Mike's retirement from the Department of Civil and Environmental Engineering at the University of Western Ontario in London, Canada, he earned a Master of Arts degree in history at Western, and now describes himself as a public historian in training. Mike, the floor is yours. Please proceed.
Good evening to those in Europe, good afternoon, and good morning to those on the West Coast. Thank you, Tanya, for that kind introduction, and thank you all for attending this tripartite civil engineering webinar. I'm here to discuss the United States-Canada International Border Survey, which is being nominated as an ASCE, CSCE International Historic Civil Engineering Landmark. This is an ideal subject for this webinar series. It's a story involving surveyors from Great Britain, the United States, and ultimately Canada. Essentially, I'll be presenting 5 pieces today. I'll start by briefly describing the historical significance of the landmark. I'll remind you that at the time of the survey, there really wasn't a meaningful distinction between civil engineers and surveyors, and I'll review the progress of the 5 phases of the boundary survey. I'll then mention some of the surveying techniques and technologies that were being used, and finally share some closing thoughts. Historical significance: the Canada-US boundary, including the Alaska-Yukon section, is the longest in the world at 5,525 miles. That's almost 9,000 kilometers. It was established by 9 formal treaties and several field survey projects undertaken primarily by British and United States boundary commissions over the course of 131 years between 1794 and 1925. Incidentally, all of the treaties were signed by representatives of Great Britain and the United States. The British Parliament passed the Statute of Westminster, granting full autonomy to its dominions, including Canada, in 1931. According to Carroll, this was the first instance of a boundary that was originally drawn on paper and then actually located on the ground. This caused some difficulties that we'll briefly discuss that the surveyors had to resolve in the field. The logistical challenges were tremendous and included operating in the remote and rugged terrain of the Maine New Brunswick forest, the Cascade and Rocky Mountains, and the perpetual snow and ice of the Alaska Panhandle. Asa C. Baldwin did not arrive at this peak on the 141st meridian by helicopter, that's for sure. Given the available technology, the survey was extremely accurate. As far as we can tell, surveying the international boundary did not have a large impact on Indigenous communities. They were often employed to assist the survey parties, particularly along the Alaska-Yukon boundary, primarily as packers and pathfinders. But the boundary itself had a huge impact on Indigenous communities, dividing and disrupting Indigenous tribal lands. I'd hope to share a list of the communities affected, but I just simply haven't the time to do that. I recently found this map created by the US Bureau of Indian Affairs and the Aboriginal Affairs and Northern Development Canada that shows, circled in red, approximately 30 transboundary Indigenous nations. That's a huge impact. At the time, there were few distinctions between civil engineers, surveyors, and architects. This 1853 syllabus from King's College, now part of the University of New Brunswick in Fredericton, gives the content of the first civil engineering program in Canada. It includes, quote, resolution of plane triangles, methods of surveying with theodolite, circumferentor, etc. Construction, use, and adjustment of the instruments used by engineers for both field and office work, leveling, method of determining the best route for railway, etc. Civil engineering involved a lot of surveying. Most of the British surveyors were Royal Engineers. In 1716, the Board of Ordnance in the Kingdom of Great Britain established the Royal Regiment of Artillery and the Corps of Engineers. In 1741, the Royal Military Academy was established at Woolwich in southeast London to train future officers. This image, dating from circa 1775, shows the original Royal Military Academy building. In 1806, the Royal Military Academy moved to new premises nearby. Many of the United States surveyors were civil engineering graduates from the United States Military Academy, which was founded at West Point, a fort constructed during the US War of Independence on the Hudson River, about 50 miles or 80 kilometers upstream of New York City. In this image, West Point is seen on the hill overlooking the river. That's a pretty sensible place to locate a fort. Would-be students apply to the institution and receive a nomination to attend, usually from a member of the United States Congress. And the USMA was the first United States college to have an accredited civil engineering program. The survey was carried out in 5 distinct phases. The first involved locating and marking the eastern boundary between the north end of the 13 colonies and eastern Canada, primarily between 1796 and 1844. The boundary through the Great Lakes to the Lake of the Woods came next between 1818 and 1825. And then the definition of the line between the Pacific Ocean and the crest of the Rocky Mountains occurred between 1857 and 1861. The boundary was filled in from the crest of the Rocky Mountains to the Lake of the Woods between 1872 and 1874. And then finally, primarily between 1893 and 1912, the boundary between Alaska and Yukon and British Columbia was surveyed. We'll work chronologically through these in a bit more detail. The eastern boundary evolved from the boundary between New France, held by France, and the 13 colonies, which were then British territories. After the fall of Quebec, the Treaty of Paris ceded New France to Great Britain. In 1771 and 72, Quebec's Deputy Surveyor General, John Collins, and Thomas Valentine of New York completed part of the Valentine-Collins line along the 45th parallel between the headwaters of the Connecticut River and Lake Champlain. In 1773-74, Collins continued the line westward along the 45th parallel to the St. Lawrence River. This cannot really be called an international boundary because the territories on each side of the line were British. A group of 79 French colonists, led by Samuel de Champlain, settled on Daucher Island, also called Ile Sainte Croix, locating in what is now known as the Sainte Croix River in 1604. Their experience overwintering was disastrous. Half died of scurvy, and the rest relocated to Port Royal. The 1783 Treaty of Paris defined the boundary to be the Sainte Croix River, but by the late 18th century, there was no river known as the Sainte Croix. The British claimed that it was the Scoodic or Scoodiac. The United States claimed that it was the Maguadavic, roughly 25 miles or 40 kilometers east of the Scoodic. In 1798, a commission decided that the Scoodic was originally the Sainte Croix based on excavations on Daucher Island in the Scoodic that revealed relics from the 1604 settlement. This is actually quite important, as suggested by the red and blue lines on the screen. Accepting the United States claim could have caused much of the upper St. John River in New Brunswick to be United States territory. The Treaty of Paris stated that the boundary would run north from the source of the St. Croix River, but this was also ambiguous because roughly 20 miles or 32 kilometers upstream from Calais St. Stephen, the river branches. The International Boundary Commission decided that the boundary would follow the northern branch in 1798. Surveyors Samuel Titcomb and John Harris marked the source a year earlier, and the monument, shown here, was further marked by a cedar post, shown on the right of this photo, and further by a cast iron monument in 1843. The next segment started at the east end of Lake Ontario and ran through Lakes Erie, Huron, and Superior to the Lake of the Woods. A prominent surveyor for the British on this segment was David Thompson, who'd retired from his fur trading career with the Northwest Company in 1812, drew his great map of the Northwest of North America in 1813 and 1814, and started surveying the international boundary, often assisted by his son Samuel, in 1815. Thompson was held in very high esteem. He was also engaged by the United States to carry out this part of the survey. David Thompson's surveying and mapping of the Northwest of North America was recognized as an ASCE/CSCE International Historic Civil Engineering Landmark in 2022. The commemorative plaque is located at Fort William Historical Park in Thunder Bay, Ontario. Thompson's achievements are particularly noteworthy because he was essentially blind in his right eye. One of history's most notable surveyors and explorers had a serious, lifelong visual impediment. The negotiators of the 1793 Treaty of Paris relied on this 1755 Mitchell map to define the boundary west of Lake Superior. Article 2 specified that the boundary be located, quote, thence through Lake Superior northward of the Isles Royal and Philippot to the Long Lake, thence through the middle of said Long Lake and the water communication between it and the Lake of the Woods to the said Lake of the Woods, thence to the most northwesternmost point thereof, and from thence on a due west course to the river Mississippi. Unfortunately for all involved, the map was quite inaccurate in this region. Ile Philippot, for example, does not exist. There's not a single river flowing directly from the Lake of the Woods through Long Lake to Lake Superior. Lake of the Woods has a much more complicated shoreline than depicted. And finally, as David Thompson had discovered in 1798, the headwaters of the Mississippi lay south of Lake of the Woods. Heading west from the northwest angle of Lake of the Woods, you'd reach the Pacific Ocean without ever crossing the river. The British claimed that Long Lake was the mouth of the St. Louis River at Duluth. The United States counterclaimed that it was the mouth of the Kaministiquia at the present-day Thunder Bay. Again, that's a huge difference of territory. In 1842, the Webster-Ashburton Treaty specified that the boundary would be the Pigeon River, something of a compromise between these two extremes. British and United States survey parties initiated the search for the northwest angle of the Lake of the Woods in 1823. The initial candidates, Portage Bay, Monument Bay, or Rat Portage, were all deemed by the Hudson's Bay Company to be too far north and would jeopardize the British fur trade route. Basically, the Hudson's Bay Company had to get furs from what is now Winnipeg to what is now Thunder Bay. And those boundary locations would have required them to take the furs through American territory to get to Thunder Bay, and that would not have been very satisfactory for them. David Thompson located a fourth possibility at what's now known as Angle Inlet, and the British government sent German astronomer Johann Ludwig Tierks to confirm that this was indeed the northwest angle of the Lake of the Woods. Just remember how straight that boundary was on the previous slide? This is what it really looks like. It's quite convoluted. So then, between the crest of the Rockies and the Pacific Ocean is this 410-mile or 660-kilometer section of the border. It's short, comparatively short at least, but it's characterized by extremely remote and rugged mountainous terrain, much of an unexplored wilderness or sparsely settled. Impenetrable, thick, tall timber and brush covered many lowland areas. Both conditions prevented surveys from being carried forward in a continuous line within the time and budget allowed, so an alternative method was devised, resulting in only portions of the line being marked on the ground. Reconnaissance and logistics became major challenges. Baker, writing in 1900, notes that thus it resulted that of the entire boundary, 190 miles or 305 kilometers were cleared and marked, and 220 miles or 354 kilometers were neither cleared nor marked. They were not traced out, cleared, surveyed, or marked. The survey progressed eastward, reaching the Skagit Valley in 1858, the Columbia River in 1859, and the summit of the Rocky Mountains in 1860. The work of clearing and marking the region between the Columbia River and the summit of the Rocky Mountains concluded in 1861. Here's a photograph of the original boundary cairn on the Kootenay River. The cleared boundary is visible. On the prairies, the work of the boundary survey began in 1872 at Pembina, with a party traveling along the Dawson Road to recover the location of the northwest angle of Lake of the Woods. They then surveyed the 49th parallel from there back west to Pembina. The first section of this survey was significantly more difficult than the section west of Pembina because the terrain is a mixture of forest and muskeg. Cut lines had to be cleared, but it was more troublesome that instruments had to be set up on swampy soil, making astronomical latitude observations difficult. Surveyors working for both the United States and British commissions developed different civil engineering solutions to this problem, including driving piles into the muskeg in search of a stable clay layer, or building elevated observation platforms using wood and/or gravel and soil. The following year, work to survey west from Pembina began. Progress on the open plains section was much faster. In general, astronomical observations made every 20 miles or 32 kilometers were connected with terrestrial surveying, aiming to link the astronomical sections with a curved line representing the 49th parallel. Terrestrial survey work and even the camps of the crews were kept to a distance from the active astronomical stations to reduce vibrations that could affect the precision of instruments. The British and American parties alternated astronomical stations and worked west over 2 seasons, reaching the Rockies in 1874. This is Albany. It's not Featherstone-Haugh, actually pronounced Fanshawe. I was born in what's now the Toronto area, but was taken by his parents to France at an early age and became an officer in the British Army. He received his commission as an officer in the Royal Engineers in 1859. His father, George William, and his brother, James Duane, were also surveyors, surveying with the British frontier surveyors at a time when most of their professional associates were military men. From 1872 to 1874, Fanshawe took charge of a British-Canadian astronomy team that included William F. King, who worked on the Alaska-Yukon boundary surveyor and later became the Dominion Astronomer of Canada. In September 1872, the party took their first latitude observations at Pembina, confirming Farquhar's finding, that was an American surveyor's finding, that the Hudson's Bay Company post there was in fact south of the 49th parallel on United States territory. Fanshawe's party spent the winter of 1872-1873 under canvas in tents when the temperatures plunged to 51 degrees Fahrenheit or 46 degrees Celsius below zero. Yet, a visitor described him as being, quote, in wonderfully good spirits as he doggedly led his team across icy swamps and muskegs, observing stars and cutting survey lines with incredible zeal and endurance. Featherstone Haugh was subsequently sent to India as an expert in submarine mining. How's that for a transition? We're going to go from astronomical surveying to submarine mining. He retired with the rank of colonel and died unmarried in England in 1902. Finally, the Alaska-Canada boundary. The Anglo-Russian Convention of 1825 fixed the boundary between British and Russian possessions in North America. In the Alaskan Panhandle, the boundary ran from Prince of Wales Island, which remained Russian territory, north along the Portland Channel, and then followed the summit of the mountains that ran parallel to the coast to the 141st meridian at Mount St. Elias. So there's Mount St. Elias, a key point. From there, the boundary followed the 141st meridian north to demarcation point at the Beaufort Sea. In 1867, the United States purchased Alaska from Russia, but the location of the proposed boundary remained vague. Significant discoveries of gold in the Stikine Valley, 1861, Cassiar, 1873, Stewart River, 1885, 40 Mile River, 1886, 60 Mile River, 1892, and obviously, particularly the Klondike in 1898, made it imperative to clearly locate and mark the boundary. In 1888, William Ogilvie marked the boundary at 40 Mile River and, in 1895, at Yukon River. J.E. McGrath of the U.S. Coastal and Geological Survey confirmed Ogilvie's Yukon River boundary. In 1906, F.A. McDermott of the Dominion Observatory determined that Ogilvie's 1888 line was only 218 feet, that's 66 meters, west of the meridian. An error of 218 feet in the location of a point on the surface of a planet is remarkable accuracy. The Alaska Panhandle was by far one of the most complicated and difficult segments of the entire boundary survey. Nearly 1/3 of the entire region is perpetually covered with snow and ice. Travel over the snowfields was usually done early in the morning to take advantage of the surface crust. Although men were roped together and carried alpenstocks, as shown here, a route that had been quite safe earlier in the day often became hazardous later, especially when the deep crevasses had to be crossed on melting snow bridges, as shown. For example, it took packers on the Davies Glacier 8 hours to travel 4 miles. This photograph shows the Grand Pacific Glacier front in 1929. The boundary line across Tar Inlet is shown by the yellow line near the bottom of the photo. Long periods of daylight in the summer aided the field work. The mosquitoes were plentiful, but the men used head nets during the day and special tents with sewn-in floors at night, which aided sleeping. Horses suffered, but smudge pots helped. Access, typically by water from Yukon Territory, was often difficult. Until late May, the lakes and rivers could be crossed on the ice. The commonly encountered rain, snow, and fog caused many uncomfortable days and nights in the makeshift camps. The United States parties mapped the topography by plane table, as shown here, while, in response to the challenging weather conditions, the Canadian parties used a relatively new method, phototopography, that we'll talk about shortly. On June 29th, 1925, so that's almost 100 years ago, a group led by Asa C. Baldwin attempted to ascend Mount St. Elias, a difficult climb for even skilled mountaineers. Bad weather forced a retreat before they reached the summit. An Italian expedition led by Prince Luigi Amadeo, Duke of the Abruzzi, successfully climbed Mount St. Elias on July 31st, 1897. The second successful ascent to the summit by the Harvard Mountaineering Club was not until 1946, almost 50 years later. Having briefly described the history of the survey, I'll switch to talk now about some of the surveying tools and techniques that were used, including portable chronometers, artificial horizons created using liquid mercury, meridian or astronomical transit instruments used with the chronometer to determine longitude, and almanacs that tabulated the locations of celestial bodies. These are all heavy things to lug around in the days before helicopters. Edward Massey of London, England, patented and made Massey's patent log in 1805. It consisted of two parts connected by a rope, the rotator or fly with the brass fins on the right-hand side of the illustration, and an engraved brass recorder on the left-hand side. Towed behind a vessel, the number of rotations of the fly indicates the distance traveled. David Thompson's parties used Massey's patent log to survey Lake Ontario in 1822 to 24, accurately measuring the distances while traveling by canoe at 4 miles per hour or 6.5 kilometers per hour. That's actually paddling pretty fast. 3 miles per hour is much more common. It would have been ideal for lake work where the currents are minimal, eliminating any need to correct for current. It's interesting to consider the evolution of astronomical surveying over the course of the International Border Survey. At the turn of the 19th century, land-based surveyors were typically using technology that had been developed for ship navigation. So this familiar C.W. Jeffreys illustration, for example, shows David Thompson taking an observation using his sextant and an artificial horizon. He's measuring the angle between a celestial body, probably the sun in this case, and its reflection on the plane surface, and dividing the value by 2 to determine the declination. The flask near Thompson's right foot contained mercury, which was pooled in the base of the device and shielded from the wind by the inclined glass to create the reflection plane. Jeffreys intentionally shows the measurement being taken some distance from the adjacent camp, so vibrations by people or animals would be minimized here. He also shows Thompson sighting using his right eye, which we've already noted was almost blind, and so this is not an accurate representation. It was difficult to determine the time accurately. This was not a problem for latitude determination. The surveyor typically took sequential sightings of the sun around noon, and the greatest angle measured corresponded to noon. Knowing the time more accurately is much more critical to determine longitude, and Thompson would determine the time by celestial observation, often observing the eclipses of the satellites of Jupiter. He would then set up 2 portable watches accurately, and as long as these remained stationary, they would remain reasonably accurate for a day or so. By the late 1850s, the United States surveyors in the Rocky Mountains used the zenith telescope and the Talcott method to determine latitude by observing the declination of pairs of stars crossing the meridian. The Talcott method provided for much shorter observation and computing time and better accuracy than the other commonly used methods of the period. The British were so impressed that they bought their own zenith telescope and employed the Talcott method for the remainder of their surveys. Danish astronomer Peder Horrebow proposed what is now known as the Talcott-Horrebow method to determine latitude in 1740, and United States geodesist Andrew Talcott implemented it practically in 1836. It involves observing with the eyepiece micrometer of an astronomical instrument the small difference between the zenith distances between 2 stars, one north and one south of the meridian, at the moment that the stars cross the meridian plane. If both stars are at upper transit, the latitude, phi, is given by the relatively simple expression shown. This image shows British Chief Astronomer and Surveyor Captain Robert Wolseley Haig, Royal Artillery, standing at the left, and Assistant Astronomer and Surveyor Charles John Darrah, Royal Engineers, seated, using the American Zenith Telescope in 1860. Note the size of the instrument that the telescope is mounted on. That's the stump of a major tree. The edge of the tent is oriented east-west to facilitate observing stars crossing the north-south meridian. Surveying of the 141st meridian started at Yukon River Crossing, where an existing telegraph connection facilitated receiving accurate time signals for astronomic observation. The signals were transmitted from Vancouver, over 2,000 miles or 3,200 kilometers away, via Dawson, and from Seattle via Eagle. The Canadian time signal probably originated at the Dominion Observatory in Ottawa, which opened in 1905 to, quote, make astronomical observations for establishing precise time signals for use across Canada. The Dominion Observatory official time signal, later the National Research Council official time signal, is the longest running Canadian radio program, commencing on the 5th of November 1939 and running daily until the 9th of October 2023. The 1892 commission appointed to study the Alaska-Yukon boundary dispute had 3 years to agree on a boundary from the Portland Canal to the 141st meridian, with the US surveying the coast and Canada surveying the mountains. Because of the difficult terrain, the Canadian Boundary Commissioner, William F. King, decided to use a new method of survey mapping, phototopography. Edward Gaston Daniel Deville, the Surveyor General of Canada, had experimented with this method of surveying in 1886 in the Rocky Mountains for the Canadian Pacific Railway. He described it in an 1891 book, quote, "A few points, including all occupied stations, are located by angular measurements. From the occupied points, photographs of the surrounding topography are taken, a complete round of the horizon usually being made from each station." So the photograph shows the camera mounted on a tripod, and there's a lazy Susan between the camera and the tripod that allows the surveyor to rotate the camera and take pictures in all directions. Devices are employed for facilitating the measurement of the horizontal and vertical angles from the photographs, and the photographs are sent to the central office in Ottawa, where maps are constructed from them. Angles are measured from the photographs, and thus all points for location are fixed, their heights are determined, and contour lines are located. Essentially, this method transfers the labor of drawing maps by plane tabling from the field to the office, where the environmental conditions are obviously a lot more favorable. From 1893 to 95, Canadian parties occupied 500 camera stations and took 2,700 photos. And between 1904 and 1912, the combined parties in the field occupied 700 stations and took 5,000 photos. This is an example of a glass plate negative of a phototopography photograph. In an office, a map with the previously located positions would be placed on a flat surface, and the photographs, or pages with prominent features transferred from photographs, would be mounted around each station. Lines were drawn on the master map from each known station to each prominent feature. You can see they're using T-squares to take the top of the mountain down to the elevation of the map so that the line can be drawn. These features would then be located on the map by simple triangulation. And with the horizontal distances known, elevation differences could be determined. Our document nominating the surveying of the United States-Canada international boundary as an ASCE-CSCE International Historic Civil Engineering Landmark is nearly complete. It's a substantial document. This slide is already obsolete. It's now about 120 pages long, 30,000 words, and 59 references. We're very pleased to have captured short 150 to 300 word biographies of 47 of the surveyors, including 21 American surveyors, 20 British surveyors, and 6 Canadian surveyors. We're now assembling letters of support. There are 13 ASCE sections along the boundary, and so far 8 of the 13 have agreed to support this initiative. We're still waiting to hear from the other 5. So in closing, this was a remarkable achievement. The surveyors of the international boundary did not have helicopters or even trucks. They didn't have GPS. They didn't have radios. They didn't have insect repellent. I have to say, I spent 3 summers with an astronomy field party of the Geodetic Survey of Canada between 1977 and 1979. We had a Ford F-150 truck with a full cab on the back, and that carried all of the stuff we needed to do the surveying. It didn't provide any accommodation or food or anything useful like that. And it really is pretty hard to imagine being an effective surveyor without having a helicopter to take these things up to the tops of mountains where your survey stations are located. So this really was quite a remarkable achievement. And the other thing that's quite neat is that throughout the 5 phases of the survey, the surveyors from the United States, Britain, and Canada consistently displayed a remarkable spirit of cooperation. There were occasional diplomatic incidents, but rarely in the field. And so, speaking of remarkable spirits of cooperation, it's been a pleasure to work with the individuals named here to pull this nomination together. All have contributed meaningfully to the final document. So with that, I think I'll say thanks for your attention. I'll stop sharing the screen and hopefully we've got some time for some questions.
Wonderful. Thank you, Mike. That was fascinating. And I learned a lot about old survey methods. So again, thank you. If you have any questions that you would like Mike to address, if you could, please put your question using the Q&A feature. Just for starters, Mike, I wanted to ask you, you started off your talk mentioning how incredibly accurate it was, considering, as you said, the rugged conditions and the equipment and logistic issues. Can you give us an example of that level of accuracy as that would compare to what we have today?
Well, that's a great question. Thanks. Ogilvy's determination of the point where 40 Mile River crossed the 141st meridian was an example of very good accuracy. The error was in the order of 220 feet, which is really very accurate. Work by Smythe in 1981 talked about the accuracy of Thomson surveys. Thomson, using the marine navigational equipment, sextants and so on, took readings at Rocky Mountain House of latitude, and he established that to within a mile. He took 19 longitudinal readings and established the longitude of Rocky Mountain House to within 5 miles. So in 100 years, we're going from 5 miles accuracy in longitude to 200 feet accuracy in longitude. That's very good. The astronomy work that I was involved with was primarily to measure the deflection of the vertical. If you think of gravity as a vector, if you have conditions where you've got high density and low density terrain adjacent to each other, the obvious answer is mountains beside an ocean, then the vector of gravity doesn't go through the center of the Earth anymore. It gets deflected a little bit. And people who are leveling instruments to be perpendicular to the vector of gravity start to get into trouble in large triangulations where the edges of the triangulations don't fit together anymore. And it's actually using corrections that are based on the profile of the geoid that you can make these large triangulation nets more precise.
Thank you. One of the questions that we have from an attendee is, have any of the monuments slowly moved over time that have now changed the boundary? And if so, how would we deal with that now?
That's a good question. I think there are a couple of things to say there. The first is that the original Collins-Valentine line wasn't all that accurate in places, and particularly at the north end of Lake Champlain, the line was about 3/4 of a mile north of where it should have been. And at the end of the 1812 war, the United States built a fairly substantial fort at the north end of Lake Champlain to discourage invaders coming down the Richelieu River. And it was discovered in the resurvey of that area in the 1840s that the fort was on Canadian territory. So after a bit of a kerfuffle, they decided that they were just going to leave the boundary where Collins and Valentine had defined it and live with the fact that it wasn't a perfect representation of the 45th parallel. Since then, agreements between Canada and the United States and the activities of the current International Boundary Commission are to maintain the boundary as best they can. So that involves presumably checking the accuracy of the location of monuments. And so I don't think that moving monuments is a very big issue in defining the boundary now.
Okay, great. We've had a couple questions on just the survey techniques from back in the 1800s and early 1900s that you described so well for us. A couple of people are interested in maybe references or textbooks. Can you share with us where you found some of that information about the old school surveying?
I can. One of the more interesting references that I found is a paper by Smythe, and I don't have the full reference in front of me here, published in 1981, that talks in detail about David Thompson's surveying and mapping techniques. There are other good sources. Chuck Binks, who's on the call, dug up a wonderful paper from about the same time that talks about the photo topography method of surveying in some detail.
Okay, thank you. I guess maybe we have time for one more question. So, you talked about so many challenges in getting this survey completed. In your opinion, what was the greatest challenge to this border survey?
So that's interesting. I guess there were several. Certainly, access to the Alaska, British Columbia, and Alaska Yukon boundary was very difficult. The surveyors were trying to use rivers. Remember, they've got a minimum of a truckload of gear here. This is a lot of stuff. And they were trying to use rivers to try to get as far as they could. And the rivers were fast and treacherous. And there are certainly stories of canoes upsetting and photographic equipment or glass plate slides that were used for the phototopography films being lost. There was even instances where, having done the survey and you're trying to get all this stuff back to the office to do the office work on it, those photographs would be lost and they'd have to go back into the field the next summer and retake them. So I think that was quite challenging. But there were really challenges everywhere you look. Valentine didn't complete the second year of surveying in the 1770s, in part because he was afflicted with something that they called Lake Champlain disease, which I guess was some kind of a waterborne irritant that kept him in bed for a while. Virtually everywhere you look, the very cold temperature conditions that were endured on the prairies, they didn't really have power tools in those days. And so whether it was the Maine New Brunswick forest or the terrain between British Columbia and Washington State or other places where there are very large trees, clearing the line would have been a major undertaking as well. So I guess there are a lot of things, and certainly what's happening in the Yukon, BC, Alaska boundary is probably the most interesting and challenging, but I don't think there's a length of the international boundary that doesn't have great stories associated with it.
Agreed. Yes. Logistically, environmentally, it was quite impressive. So it's fairly evident why your team put together an application to make it a civil engineering landmark. So again, thank you, Mike, so much for your presentation today. So again, thank you for your attendance today. We appreciate it. We look forward to seeing you again in September and have a pleasant couple of months in the meantime. Enjoy your summer. Thank you.
The new transatlantic cable webinars are coordinated by a tripartite ad hoc committee that includes the individuals listed here.